Hi everyone. So in this topic, I want to discuss basically how we visualize or interpret the wave function or what the wave function means. And remember that when I use the word wave function, I'm really just talking about the orbital. So these two words are interchangeable. And so you want to be able to use both terms interchangeably, either orbital or wave function. A lot of times in textbooks you'll see this term orbital, you don't see the term wave function as often, but just understand that those two terms are interchangeable. So going back to the previous video when we talked about quantum numbers and the solution to the Schrödinger equation, we talked about the idea that when we solve the Schrödinger equation for a particular wave function, okay, or a particular orbital, we get a certain set of solutions and a unique set of numbers, and those are what we call quantum numbers. And remember that we have the principal quantum number, which is n, the angular momentum quantum number, which is L, and then the m sub L, which is the magnetic angular momentum quantum number. Now, when you have a wave function, a specific wave function for an atom is labeled with its n, L, and m sub L designation. So for example, I can say I have the wave function or psi 1, 0, 0, and what that means is this is psi where the n is equal to 1, okay, the principal quantum number is equal to 1, the L is equal to 0, and the m sub L is equal to 0, okay? If you interpret this, again, going back to the previous topic when we talk about quantum numbers, you can look back at that video again. You know that this 100 corresponds to the 1s orbital, right? Because 1s is n equals 1 and L equals 0, okay? And if L is equal to 0, m sub L has to equal 0, okay? You can also talk about the psi 200 orbital or psi 200 wave function. And really, when we say that, we're really just talking about the 2s orbital, okay? So what I, again, want to clarify here is the fact that you can talk about an orbital either as the name like 2s, for example, or you can talk about it in terms of psi, n, L, and m sub L designation here. You can talk about psi 210. In this case, if you look at it, n is equal to 2, which means there's a 2 in the front. L is equal to 1. Now remember that when L is equal to 1, that's what we call a p orbital. And then the m sub L in this case could be -1, 0, or +1. As it happens for this particular wave function, the m sub L is equal to 0, and that's what we designate as the 2p sub z, 2pz orbital, okay? And so on and so forth. So you can have, both types of ways of denoting your wave function or your orbital. Again, the one that you're probably most comfortable with seeing before from prior chemistry courses is this designation, which is the 1s, 2s, 2p, 2pz, 3s, 3p, 3d, and so on. But just know that you can also write those same orbitals with these symbols right here, with the wave function symbols. Now, one of the things that we talked about when we first introduced the idea of quantum mechanics is this interpretation of the square of the wave function as representing the probability of finding an electron in the three-dimensional space that surrounds the nucleus. Okay? This is what we refer to as the Born interpretation of the wave function. Born. Max Born is the scientist who came up with this concept of interpreting the wave function as a probability density, the square of the wave function. And that turns out to be the most experimentally supported way of interpreting the wave function, because when Schrödinger came up with the wave function, he didn't necessarily have a physical interpretation of what the wave function should be. He just knows that if you use these wave functions, you can describe the electron, the properties of the electron. But Born came up with this interpretation that the square of the wave function should be the same as the probability of finding electron in three-dimensional space. So again, that's what we're going to talk about in this topic. Is we're going to talk about how we represent this probability, because we're talking about probability density. So we're talking about the fact that around the nucleus you're going to have different spaces where you might have a higher probability of finding the electron in one space versus another space. So what we're going to talk about is how we represent this probability, both in terms of a drawing and in terms of a plot in a graph. Okay? So the first way to represent the probability density, in other words, the way to represent psi squared, is the one that you see right here. And this is probably something that you're somewhat familiar with. You might have seen it before. And this is called the electron density dot representation. Okay? It's dot because you can see that there's a bunch of dots here. And this is a very easy one to understand because you have a three-dimensional axis. The nucleus is always at the center. And then the atom itself, of course, is represented here by the electron density, okay, which is this blue dot, a bunch of dots here that are blue, and all that represent the electron density. So, as it says here, the density of dots is proportional to the probability density, or proportional to psi square. Way to interpret this very easy: the more dots, the higher the probability of finding the electron in that position. So this particular one is for the 1s orbital. Okay, so not every orbital is going to look like this, but for the 1s orbital, the density dot representation look like this. And as a result, you can interpret this to mean that as you go further and further away, r here is the distance between the nucleus to a certain point away from the nucleus. So as you go further and further away from the nucleus, you notice that the dots get fewer and fewer, which means that the probability of finding the electron decreases tremendously as you go further away from the nucleus. Okay? And in fact, for the 1s orbital, you can calculate the highest probability of finding the electron is near the nucleus, not at the nucleus, but near the nucleus. And the distance is the distance where you can most likely find the electron is called A naught. Okay, this is the symbol. And it's actually calculated to be 52.9 picometers. This has been verified experimentally. The interesting thing about this calculation, and we'll talk a little bit more about this value a couple of slides later, but the interesting thing about this calculation is that this was this was obtained from using the wave function approach, which is the quantum approach, right? The Schrodinger equation approach. But it turns out that, remember that Bohr, the Bohr model works for the hydrogen atom, so he was actually calculating the distances for the Bohr orbits. Remember that there's different Bohr orbits for the electron in the hydrogen atom. And the ground state orbit, which is the n equals 1 orbit in the Bohr model, had a distance that is also equal to 52.9 picometers. So that's interesting because we know that the Bohr model is valid for predicting the properties of the hydrogen atom because it actually works for one electron systems. But the quantum model, but the Bohr model fails for the multi-electron system. However, it turns out that when we do this calculation for the hydrogen atom using the quantum model, we have exactly the same result, which basically is a support to the idea that quantum mechanics is a valid approach of modeling the atom, because even though you're modeling the electron as a wave, you're actually getting the same value that Bohr obtained from his particle approach to calculating the radius of the electron in the ground state. Okay, so that's for the 1s orbital. You can do this again, but for a 2s orbital. Now, this is the electron density dot representation for the 2s orbital. You can see that this is actually, if you were to run a simulation, you calculate, this is what you'll see. And as you can see here, most of the electron density is located in this radius away from the nucleus. The nucleus is this black dot right here. you have density all over the place, but some parts are a lot more dense than others. This is obviously the densest. There's a little bit dense part right here closer to the nucleus, and then as you go further and further away, the density decreases tremendously. One of the things I want to point out here is that you can actually draw this, less of a mess, in less of a messy way, by drawing it this way. Okay, so if you draw it this way, this is your three-dimensional axis. The nucleus is still in the middle. Now you notice that basically the 2s orbital has two regions with dots where you can find the electron. One is close to the nucleus, the other one is a little bit further away from the nucleus, but that's the one that is larger in terms of probability. Okay, and what's interesting if you look at this representation is that you notice that there's a white region in between those two colored regions. The white region here represents a node. Remember that a node is a region where the electron density, the wave function has a value of 0. So the square of the wave function is also 0. Okay, so this node region implies that there is no probability of finding the electron in between these two spaces. Okay, between the two non-zero areas. That's always interesting to kind of think about, because if you think about a particle, and some people think about this as a particle, then then it's really hard to imagine how can a particle exist here and exist here but somehow not exist in between. How does it go from one region to another? And that would be the wrong way of thinking about it, because remember that we're modeling the electron as a wave here. So in a wave representation, it's possible that you have a wave in one part, no wave in the other part, and then yet another wave in certain parts. Okay? Remember we talk about these constructive and destructive interference, so it's possible that you can have, signal in one side, no signal in another side, and another, and signal in some other part. So it doesn't at all, it doesn't at all conflict with the wave model of the electron. But if you think about it from a particle perspective, then you can get really confused. Another thing to note about the 2s orbital is also larger than the 1s orbital. And the reason for that, of course, is because remember that the n is equal to 2 here, and n, the principal quantum number, is a measure of the size of the orbital as well as the energy of the orbital. So the fact that the n is equal to 2 here tells us that this is a bigger orbital than the 1s, and also at a higher energy level than the 1s orbital. However, the shape of the 2s orbital is exactly the same as the 1s orbital, which is this spherical shape, because they're both s orbitals. They both have the L, which is the angular momentum quantum number. Remember, that's what tells you the shape of the orbital. Both of them have L equals 0, and that's why the shape of the 2s and the 1s are exactly the same.